Now that we know what normal modes are, I'm going to make this statement. Each vibrational normal mode has associated with it an irreducible representation. Okay, so how do we try to figure out, given a normal mode, what the irreducible representation is? Well, here's a procedure here. What we do is we draw vectors representing the vibrations of an atom in a molecule. And then that molecule belongs to a particular point group. We perform the symmetry operations of that point group and keep track of where the vectors point. If the vector actually changes direction, if it points in one direction, but then after the symmetry operation it points in another direction, and then the character of that particular operation is -1. We do that for all the symmetry operations of a group, and then we have a list of characters, and we associate the characters with some irreducible representation. Let's go through this example and we'll see what we mean by that. What are the irreducible, irreducible, clearly I've misspelled that. What are the irreducible representations of the three normal modes of water? Why does water have three normal modes? Recall that the normal modes is 3. Let me rewrite that there. The number of normal modes is 3n-6 for a nonlinear molecule, which water is. Water has 3 atoms, so that's 3 times 3 minus 6, and that is equal to 3. So water has 3 normal modes. Well, let's look at the normal modes. What here I have a computational chemistry program, Hyperchem, and Hyperchem will compute the normal modes. So let's do this. It's calculating. It's done. Now let's look at the normal modes. And Hyperchem labels these 1, 2, and 3, and it gives you the IR spectrum 1, 2, and 3. All right, let's look at normal mode 1. Okay, there is normal mode 1. Now what we have to do is associate this vibration with some vectors. All right, let's start it now. So this vector will be pointing down this way. This vector will be pointing down this way for that hydrogen atom, and this vector will be pointing up there. So now what we have are where the vectors point for this particular vibration. Okay, so let's draw that. Here's the water molecule, here's the H, and here's the H. So we said this vector will point that way, that vector will point that way, and that will point up here. Now if we look at the C2V point group, water belongs to that. There are 4 symmetry operations that we can do on the water molecule in the C2V symmetry: E, C2, sigma V, and sigma V prime. So let's see what happens to the direction of those vectors each time we do one of these symmetry operations. And recall sigma V, that's in the XZ plane, and sigma V prime, which is in the YZ plane, and the molecule is in the YZ plane. The z-axis is the principal rotation axis, and therefore the x-axis would be coming out towards you. All right, let's do the E operation. Well, nothing happens, so the character of that is 1. Let's do a rotation about the C2 axis. This vector won't change, it just lies in the rotation axis. But let's look at this. This hydrogen will go over there, but if you rotate this, this hydrogen is pointing this way. When you rotate it, it'll be pointing that way. And this hydrogen, when you rotate it 180 degrees, it will be pointing in. So nothing changes with regard to the direction of these vectors. So that character there would be 1. Let's look in the XZ plane. That's the plane coming out towards you, containing the rotation axis. Well, if we reflect that in there, it'll point the same way. This one reflecting over here will point the same way. And of course, this vector being in the plane, when you reflect it, won't change. So it looks like the character for that is 1. And finally, let's do the sigma V prime in the YZ plane. That's the plane of the molecule. Well, all vectors, nothing changes there, so all vectors will point the same way. So that is 1. Then we go to the character tables a 1, 1, 1, 1. That's the A1, the totally symmetric irreducible representation. So this then would be an A1. So the irreducible representation corresponding to this normal mode is A1. Okay, let's take another look. Let's take a look at another rotation. Another vibration. Let's look at normal mode, which Hyperchem is calling 2. Okay, here's the normal mode. Looks like it's a stretch. It's a symmetric stretch. So let's draw the vector going out this way. Okay, and the vector going out this way. And then this oxygen atom, the vector will be going up. So that's the normal mode. So let's take a look and see what that will do with the symmetry operations. So we said the vibrations are going to go this way, so the vector will go this way, that will go that way, and that will go up this way. Let's look at the symmetry operations for this particular normal mode, V and sigma V prime. Well, the E, nothing happens there. If we rotate about the principal rotation axis, that vector is pointing this way. When it rotates over here, it's still pointing the same way with this one. That's going to be a 1. Let's look at the plane, the XZ plane that's coming out towards you. If that's reflected there and that's reflected there, the direction that the arrows point don't change. So that's also a 1. And the sigma V prime in the plane of the molecule, yes, the vectors don't change there, so that's a 1. So the irreducible representation corresponding to this normal mode is a 1. All right, let's ask the Hyperchem to give us the last normal mode, vibrational spectrum, normal mode, which calls number 3. So this looks like the asymmetric stretch. Okay, that's stretching while this is compressing and back and forth. So let's start our vectors here. So this will point out. Okay, start our vectors here. That will point in, and the oxygen molecule will go over to the right. So that's out, in, right. Okay, we draw that normal mode here. This will go out, the asymmetric stretch. This will go in, and this will go, well, we said we had, I think I got right and left mixed up. Anyway, it goes that way. So we have E, C2, sigma V prime. E close to be 1. Now, here's the rotation axis here. If we rotate 180 degrees about this oxygen molecule, actually, yeah, I think that was right. This has to go this way. Sorry. Maintain the center of mass unchanged. So if we rotate about this rotation axis 180 degrees, that vector is now going to be pointing the opposite direction. This vector, which is pointing this way, will now point that way. This vector will point up, so the direction that these vectors point after the 180 degree rotation will be changed by the direction will be changed. That, instead of pointing right, will be pointing left. Instead of going, this one, instead of going up after rotation, will go down, and this one, which is now going up after rotation, will go down. So that's a -1 in the character table. If you look at the XZ plane, the plane coming out towards you, we reflect that. It looks like the direction of the arrows change. That's also a -1. And then in the plane of the molecule, nothing changes when we reflect in the plane, so that'll be a 1. We go to the character table. 1, -1, -1, 1 is a B2 irreducible representation. So that's how one associates a particular normal mode of a molecule with an irreducible representation. Now let's go on. Here's a key point. A normal mode will be infrared active if it has the same irreducible representation as one or more of the Cartesian coordinates. So why would that be? Qualitative explanation. Recall that the intensity of a infrared absorption is given by the transition dipole moment, which we defined as the integral over all space of the complex conjugate of the wave function of the final state, dipole moment operator, times the wave function of the initial state, integrated over all space. And we could say we could use symmetry arguments to determine whether this particular integral will be 0 or not by associating the terms in the integrand here with an irreducible representation. All right, so let's look at the dipole moment operator. Dipole moment operator corresponds to the dipole moment mu, which is equal to, say, ax. We'll write this in terms of the x, y, and z components, plus by plus cz, where these are unit vectors in the x, y, z. I guess we used ij and k before. This is associated with an irreducible representation. Say this will be the gamma, how the x-axis transforms, or gamma how the y-axis transforms, or gamma how the z-axis transforms. So the symmetry associated with the x, the y, and the z Cartesian coordinates in a particular point group, that symmetry will be associated with the dipole moment symmetry. What this implies is that the irreducible representation of the wave function of the initial state has to be contain either gamma x, gamma y, or gamma z. And this then will be associated with a normal mode. If it's not, otherwise, if this case is not the case, if the normal mode doesn't have x, y, or z in it, then wave function associated with the irreducible representation associated with the initial, with the dipole moment operator, will be equal to 0. Okay, but why is that? Well, the irreducible representations form an orthogonal set. And if, for example, this does not have the same irreducible representation as x, y, or z, then when you try to do this product will be an irreducible representation of two different rows in the character table, and what that will mean will be the integral will be 0. You have to have the symmetry of the x, y, or z axis in here so that when you multiply it by here, you will get something not equal to 0. Otherwise, it will be equal to 0. So that's a qualitative explanation of why a normal mode has to have the same irreducible representations as one or more of the Cartesian coordinates. Let's apply that to the water molecule and see which one of these would be infrared active. All right, let's look at A1 in the character table. A1, if we go down here to this crutch, A1, the z-axis transforms or has irreducible representation A1, as does that particular normal mode. So therefore, when you do that integrand, that will not necessarily be equal to 0. So this then would be IR active. And A1 also IR active. Let's look at B2. B2 in the character table for C2V, that the y-axis also has B2 symmetry. So this means that since this normal mode has B2 and the y-axis, one of the Cartesian coordinates, has B2, that means that this will be IR active. So good. So far, so good. Let's do a couple more examples here. Let's look at the normal mode vibrations of carbon dioxide and see which can be observed by infrared absorption spectroscopy. Here I've asked the computational chemistry program to compute the normal modes of carbon dioxide and calculate the vibrational spectrum. Let's just see what we have. So here's one normal mode, and it looks like this is an asymmetric stretch. So when one oxygen goes out from the carbon, another oxygen comes in from the carbon. Let's look at another normal mode. Let's look at this one here. And this looks like a symmetric stretch. All right, let's write on here what those two normal modes are here. We had the symmetric stretch, where this went out this way, that went out that way, and the carbon remained the same. We also had the asymmetric stretch, where say this carbon went that way, that oxygen went that way, the carbon went that way, and that went that way. Now let's see if we can figure out what irreducible representation each one of these vibrations corresponds to. Well, if we look up in, or do various things, we'll, or maybe remember that the point group for this linear molecule where you have one atom in the center and then equal atoms on either side. That'd be d infinity h. Now let's look at d infinity h. Here's d infinity h. It has, since it's a linear molecule and has an infinite number of symmetry operations associated with it, let's just write these down. E, C infinity, sigma v. That's E, C infinity, sigma v, I, S infinity, and C2. I, S infinity, and C2. And recall the z-axis will be along the principal rotation axis, and the principal rotation axis is the one that has the most rotations, and here it is, C infinity, that's quite a few rotations, so this would be the z-axis here. Alright, so as we rotate, let's look at this here. We'll call this totally symmetric, so we'll do the operations for the symmetric stretch. If we rotate around here, the arrows still point in the same direction, so that'll be 1, and of course the E will be 1. Sigma v, that's a plane in the plane of the plane containing the principal rotation axis, and we see there's a plane coming out towards you, for example. Of course there's an infinite number of them, but let's look at this one. The direction of the arrows don't change in reflection there, so that'd be a 1. There's an inversion center right there in the middle, so if we invert this, that arrow will point that way, invert that way, that arrow will point that way, no change in the direction of arrows, so this will be a 1 here. The S infinity axis will be you rotate around this way and then reflect through a plane perpendicular to there, nothing changes. Same way with the C2 rotation axis, this is C2, we'll rotate around this way. And if we rotate C2 180 degrees, arrows still point in the same direction, so that's all 1s. The all 1s is called a sigma G plus. So this is the irreducible representation corresponding to this vibration is sigma G plus. Let's look at this particular vibration. Okay, if we rotate around the z-axis, nothing happens. The arrows still point in the same way. Oh, we forgot the 1 here. That'd be a 1. The sigma v, again, a plane containing the z-axis. There'll be no change in the direction of arrows. That'll be a 1. But the inversion center, all right, this is pointing this way. Now, if we invert that, the direction of the arrow is going to point, so it's going to point the opposite way. Same way with this arrow, if you invert it through here, it'll be pointing that way and so on. So it looks like the inversion through this center will change the direction of the arrows. This would be a -1. Let's look at the S infinity axis. Here's the S infinity axis, the z-axis. We rotate there and then we reflect in a plane perpendicular to that. It looks like, oh, so that arrow is now going to be pointing that way, the opposite way, this way. That arrow will be pointing in as we reflect it, or sorry, out as we reflect it, same way with this arrow. So that looks like a -1. And let's rotate around this axis here. This is a C2 axis. All right, that arrow now will be pointing in. This arrow, when you rotate it around here, will be pointing out. And the direction of that arrow will change. So this is also a -1. So we got 3 1s and 3 -1s. Let's see. Here it is. 3 1s, 3 -1s. So that's a sigma U plus. Sigma U plus. Recall that the subscripts G and U stand for Gerada and Ungerada. Gerada means a +1 with respect to inversion. Yeah, +1. Ungerada means -1 with respect to inversion. Yes, -1. Looks like those symbols are correct. And this was the antisymmetric or asymmetric stretch. All right, so we got 2, but recall that CO2 is a linear molecule, so we have 3 times 3 minus 5, or 4 normal modes. So let's go back and see if we can see the other 2 normal modes. Then we're going to go here, this normal mode, see what this looks like. I don't know if you could see that, but here the carbon is coming out and then going into the plane, coming out and going into the plane. And as the carbon comes, now it's coming out of the plane, the oxygens are going into the plane being the plane of the screen. So this looks like these two oxygens are coming out towards you and the carbon's going in with you, and now the oxygens are going away from you and the carbon's going towards you. And the last normal mode, let's look at that one. It'll be this one here. It's just like the previous one, except that instead of these oxygens coming towards you and away from you, and the carbon going away from you and towards you, now that rotation vibration has been rotated. Now that is occurring in the plane. So these are going up and down here. That's going up and down. If you rotate this 90 degrees, then these would be coming towards you and away from you, as with the carbon. So those are the four normal modes of carbon dioxide. We already have those two. Let's take a look at the others, the other two. So let's draw it this way. So here we have carbon, double bond O there, double bond O there. And let me draw the z-axis this way. All the atoms are in the z-axis. And then here on this, we'll make the x and y axes come out this way. And over here on this oxygen, we'll do the same thing. X and y. So vibrations along the, say, the y-axis. So this oxygen will go that way, that oxygen will go this way, and then the carbon will continue along the y-axis but go in the opposite direction. So this oscillates in the y-axis, this oscillates in the y-axis, and so does the carbon. Now for that other axis, this oxygen will oscillate in the x-axis, as will this oxygen and the carbon also. So those last two modes of the vibration of carbon dioxide can be combined this way. Note that those two modes were degenerate. The two modes along the y-axis and along the x-axis are degenerate. They have the same energy. They're the same kind of vibration. So since they're degenerate, we expect to find if we now do the E operation, we expect to find a 2 in there, because that corresponds to the degeneracy of the vibration. So let's take a look here and see if we can find the degeneracy of 2. Oh yes, here we got two of them here. Listed here. We got a pi u and a delta u. All right, each one of those is twofold degenerate, corresponding to the two degenerate vibrations here. All right, well, let's go ahead and take a look at these. What's the difference between the pi u and the delta u? Well, not much, except that this is a 2 in here. This gives us a crutch here. The x and y axes transform as a pi u, and the vibrations here on the x and the y, they're degenerate. You have to couple them. They also transform as the x and y here. So it looks like our choice should be, for the irreducible representation of these degenerate modes, should be a pi u. So over here we find that the pi u ungerade, which means a minus sign, this is the irreducible representation for this particular normal mode. So now, to summarize, the irreducible representations corresponding to the four normal modes are a sigma g plus, a sigma g, that'd be a sigma u plus, and the last two modes are combined, degenerate, into a pi u. Now, which one of these corresponds to a infrared absorption? Or you go along here, looks like the sigma g plus does not have any single coordinate, x, y, or z Cartesian coordinate, so this is not IR active. Let's look at the sigma u plus. Sigma u plus, the z-axis transforms as that, so this would be IR active. And we find that the pi u, transforms, there's the x and the y, this will also be IR active. So of the 4 normal modes, in fact, we'd only see peaks in the IR absorption spectrum because this would be a single peak. It's degenerate, same frequency or same energy. Only 2 of those would be IR active, and the third would be not IR active. So finally, going back to our question, which normal mode vibrations can be observed by infrared absorption spectroscopy, which are IR active? Using these symmetry arguments, we find that those, except for this totally symmetric, this vibration is not IR active. This one is the asymmetric stretch, as is this degenerate XY motion here. All right, now another way to look at that is to just look and see what vibrations produce a fluctuating dipole moment. So really we don't have to go ahead and do all this symmetry arguments here. In fact, what we just do is look at which vibrations give a fluctuating dipole moment. All right, there's that. We'll look at the asymmetric stretch. So this will stretch that way, that'll stretch that way, that'll stretch that way. And then we'll look, let's actually do, this is degenerate, but we'll just draw one of them, where this oxygen goes up, that goes up, and this carbon goes down. All right, this you see before the vibration, when the bonds are at the atoms are at the equilibrium position, carbon dioxide does not have a dipole moment. If this goes out this way and this goes out that way, with the stretch, carbon dioxide still doesn't have a dipole moment. So this, based on fluctuating dipole moment arguments, is not IR active. Now let's look at this one. Well, initially carbon does not have a dipole moment, carbon dioxide does not have a dipole moment, but if this stretches this way and these two stretch that way, this does have a dipole moment, and that dipole moment will fluctuate as the atoms vibrate. So this then would be IR active. And finally, clearly here, I mean, without the vibration, carbon dioxide has no dipole moment, but if this goes down, those two go up, you do have a fluctuating dipole moment, so this is IR active. So we could have used fluctuating dipole moment arguments instead of symmetry arguments to conclude that the totally symmetric is not observed, but the other two is observed or are observed in the infrared spectrum. So as a final example, let's look at HCN and try to figure out which normal modes of HCN are IR active. Okay. So HCN, let's go ahead and use the fluctuating dipole moment, although we could go through the analysis. If we want to go through an analysis, so if we want to go through the arguments, the symmetry arguments, this is a C infinity V molecule. But let's do fluctuating dipoles and see if we can get the normal modes. So we have H, C, and then we have a triple bond N. And it's a linear molecule, so we expect 3 times 3 minus 5 for a linear molecule, 4 normal modes. All right, let's do the symmetric stretch, just like was done for the carbon dioxide molecule. Since nitrogen is more massive than hydrogen, we're going to have to move the carbon this way to maintain the center of mass. Now let's do the other. Another one here, H, C, triple bond N. Let's move these two together like we did for carbon dioxide, and then this one will have to be moved out this way. And this is a symmetric stretch, this is the asymmetric stretch, and then finally we have that bending C triple bond N, where let's put this one up, and then this one then will come down. So let's look and see which are fluctuating dipole moments. Well, HCN has a dipole moment to begin with, but maybe you can see if this carbon and hydrogen move this way and this nitrogen moves this way, the dipole moment will change. So as this vibration occurs, we'll have a fluctuating dipole moment, and this then will be IR active. Let's look at this one. Well, by the same arguments, HCN has a dipole moment, but as you start the vibrations, you get a fluctuating dipole. So this would be IR active. And this may be easy to see. You have a linear molecule of a dipole, but if these two go up and that goes down, then your dipole will change. So as the vibration occurs, you have a fluctuating dipole. So this would be IR active. And recall that this is degenerate. So even though you have 4 normal modes, 1, 2, 3, you only have 3 peaks in the IR spectrum. So the answer to the question is, which normal modes? All are IR active. And this is asymmetric, stretch, and the bend are IR active. All right, so that's how one looks at all right, so that is how one looks at which particular vibration will give you a peak in the infrared spectrum. You could do arguments based upon fluctuating dipole moment, or you can go ahead and for each dipole or each vibration, each normal mode, get an irreducible representation of that, and then see if that irreducible representation is the same as one of the 3 Cartesian coordinates.